Okay, this is a continuation of examples from section 4.2, 4.3, and 4.4 over synthetic division and finding real and complex zeros of polynomial functions. Something that we learned about after doing long division is that if you have something called a factor, so say you've got a polynomial and x plus 1 is a factor. That means that the zero attached to that is x equals -1. Essentially, if you set it equal to 0 and solved for x. So we know that if you have a factor, you have a 0 attached to it. And if you have a 0, there's a factor attached to it. There's a theorem that says if you plug this number, this 0, into the polynomial, it will come out with a remainder of 0, which means that when you evaluate it at -1, for this example, for saying, that would mean that your polynomial has a factor of x plus 1 if this comes out to 0 when you evaluate. So it's kind of complicated to say, but hopefully you'll see what I mean in a second when we do an example. So it says use the factor theorem to show that x minus c is a factor of f of x. So a lot of students, they do these problems and they don't understand what they're actually proving. Essentially, you're just plugging in f with 2 inside because we're going to do b part. You're doing f of 2, f of c. So here's what really is going on though. If c is 2, then x minus 2 is the potential factor we're looking at. So every time you have a C, there's a potential factor attached to that, and you just find it by thinking of what would happen if I tried to move that back over. It'd be a -2. So if we can prove that when we plug 2 in here, we get a 0, that means that x minus 2 divides evenly into this polynomial. And that's actually very powerful for us to know that. So 2 to the 4th minus 3 times 2 cubed minus 2 times 2 squared plus 5 times 2 plus 6. 2 to the 4th is 16. 2 to the 3rd is 8. 2 to the 2nd is 4. And I'm going to go ahead and work out 5 times 2 and bring down the 6. I still have some multiplication. That would be minus 24 minus 8 plus 10 plus 6. 16 minus 24 is -8. -8 take away 8 more is -16. -16 plus 10 is -6, and -6 plus 6 is 0. So that means that 2, since when you plugged 2 into the function and got a 0, that means that x minus 2 could be factored out of this polynomial. That's what the factor theorem tells us. So then next, what we had to know, because this is one piece of what we're going to be doing in this section, we needed to know a quicker way to do division. Synthetic division is where we look at division without the x's, essentially. We just look at it as numbers and the coefficients. But the problem with synthetic division is you have to use it only when it's allowed. Synthetic division is only allowed when you're dividing by something that is x to the first and then some constant over here. So you have to be dividing by x to the first for this to even make sense. Now, I'm not going to go through the steps that they had outlined in the notes again because I want to just jump right in and do some practice problems. So looking at this one, we're looking at a part here. When you want to do synthetic division, first of all, check to make sure you're dividing by something that's x to the first, which we are, because we're taking this polynomial and dividing it by x plus 4. Your next step is to turn the factor into, or polynomial, we should say. It might not be a factor. It's only if it's a remainder of 0 if it's a factor. So turn the polynomial into a root. That's an easier way of saying that. So we say x plus 4 equals 0, and we move that over. Now, why this is better than long division is because that will actually allow us not to worry about changing our signs. We've already changed signs essentially. So we put this -4, because that's what this answer to this would be if it was 0, into a box. We take the coefficients from our polynomial, making sure every power of x has been taken care of, and we place those in the row across. just as if we were doing long division, but usually we would have our x's there as well. The first step in synthetic division is to pull down the coefficient of the leading one from that polynomial, and you write it down here. You then multiply that by the number in the box, so -4 times 3 is -12. We then add the column, that's -16. We multiply -4 times -16 next. That would make +64. We add the column, that's +63. Lastly, we need to do 63 times the -4, which is -252. And this final column actually ends up being your remainder box. So if we add that to 8, we get -244. Now let me explain to you what you just discovered. What we first of all discovered is that this polynomial, x plus 4, does not divide evenly into this polynomial. So if we were trying to factor that first polynomial, this would not be a good polynomial to try to pull out. It's not going to go evenly. The second thing is we've now reduced this down to what we call a division algorithm. So this is now 1 power less than what it started with, because remember we divided by an x to the first. So we divided out an x out of each of our answers down here. So this is now 3x squared minus 16x to the first, which would just be 16x, and then plus 63. That is our quotient. Our remainder is the number in the final box, and it's by what we divided by, which was x plus 4. So remember, that's how we were writing this with long division. Another way of writing it, depending on how they ask for it, is sometimes they just ask you for the quotient and the remainder. If they just ask for the two pieces, you just write the first one as the part that was out here, and the remainder is always what was left in that last box. So two different ways of writing the same answer. Okay, let's do another synthetic division. So let's look at C part, because some of these were done in class. So for C part, we first need to start off by figuring out what this would be. First of all, it is x to the first, so we're good to do synthetic division. So that would be +3. So that's what we're going to be putting in our box. We place our coefficients. Now notice, this went from x to the fourth, but we're missing x to the third and x squared. Those are missing. When you're missing a power, you have to put a 0 in for a placeholder. Then we have a 10 and then a -3 for x to the first and no x. We bring down the first one, and then we start our process of multiplying. 3 times -2 is -6. Add the column. 3 times -6 is -18. Add the column. 3 times -18 is, not sure, we'll figure it out though, -54. Add the column. So that would make 44, and then 3 times 44 is 132, and then add the column, so add the -3 to that. So it's 129. Notice this started with x to the fourth, so we're going to be down to x to the third since we divided out 1 power of x. So this would be -2x to the third minus 6x squared, because I'm pulling that right off down here, minus 18x plus 44. That's my quotient. My remainder is 129. All right, so now we're going to do these. So example 3, they've already solved for C for you. So if they've already got this so that it's not a polynomial anymore, it's not like an x plus something, if they've already got it as C equals a number, they've pretty much done step 1 for you. So you're just putting this into the box and going straight away. So we have a -1, this would be a 4, this would be a 1, and we are missing the non-x column, so we do need to think about that. So pull down the first one, -1, multiply, that's +2, add the column, multiply, add the column, multiply. So that would be 22, and then add the column. Okay, so then this would be -x squared, because that's this first term, plus 6x minus 11, that's my quotient, and my remainder would be 22. All the yellow highlighted ones, remember, we did in class. So let's look at this next one right here. Use synthetic division to show that C is a 0 of f of x. In other words, we're trying to actually prove this time that the remainder does equal 0. So they've already got C solved for us, so we put that in our box. 27, -9, 3, 6, and 1. Notice each power of x was there, so no zeros were needed. Pull down the 27. -1/3 times 27 would be -9. Add the column. -1/3 times -18 would be +6. Add the column. -1/3 times 9 would be -3. Add the column. -1/3 times 3 is -1. Add the column. Notice that this equals 0. What that means is that this divides evenly into this polynomial. So if you turn that back into a factor by moving it over, you would notice that this is actually going to divide evenly into that polynomial. We'd be able to factor it. So 27x to the third minus 18x squared plus 9x plus 3 is the quotient, and the remainder is 0. Okay, so then we covered quite a few of these together. We did example 3 together in class. We also did example 4 in class together. And example 5, we did part A, so we're going to look at part B. So it says show that the following functions have no rational zeros. What we learned is that if you have a polynomial that has a degree higher than 2 and you want to see if it's factorable even over imaginary numbers, so just factorable in general, what we can do is find out a potential rational root theorem, essentially. So this is called our C's over D's. C's are factors of this number and D's are factors of the first number. So factors of 7 will be my C. Now when you write your factors, we don't know how this became a +7. We don't know if it was a negative times a negative or a positive times a positive. So we write all factors of 7 with a plus or minus, so 1 and 7. Then we have our factors of D, which is our leading coefficient, which is 2. So it could either be a plus or minus 1 or a plus or minus 2. Your potential list, the list that we're actually going to try to exhaust in a second to prove that none of these are going to be rational zeros. This list comes from putting all the C's over all the possible D's. So 1 over 1 would just be plus or minus 1. 7 over 1 would be plus or minus 7. 1 over 2 would be plus or minus a half. And 7 over 2 would be plus or minus 7/2. So that would be my entire potential list. Now for this polynomial to be factorable for us, we have to be able to find one of these to be equal to 0 so that it divides evenly into the function. So the way we test for that is we just plug it into the function. Now I'm just going to write what each of these would look like, and then I'm going to use the calculator to find the answers, because this could be time consuming, and the whole idea is just to make sure you understand why this has no rational zeros. So I'm just going to write in what each of these would look like, and then I'll use the calculator to prove that none of them equal 0. So notice I'm just rewriting the function over and over again with the next number in the list. So +1, -1, +7, -7. Plugged in for x. F of 1/2. F of -1/2. So there's actually 8 different things we have to show do not equal 0 to prove that we can't go any further with this problem. F of 7/2. This would be a good reason to not leave your calculator at home, especially the fraction ones. You don't want to do those by hand. All right, so let's start with the first one. 2 times 1 to the 5th plus 3 times 1 to the 3rd plus 7 equals 12. And that is not 0. So that means that number positive 1, which ties to a specific factor of x minus 1, that means that does not divide into our polynomial even. So then we do negative 1. So 2 times negative 1 to the 5th plus 3 times, oops, got to restart over. The bad thing about doing this while you're talking is that you have to pay attention to what you're typing. So negative 1 to the 5th plus 3 times negative 1 to the 3rd. Notice I'm putting it in parentheses every time I use a power, plus 7 equals 2, so also not 0. Now we're going to plug in positive 7. 2 times 7 to the 5th plus 3 times 7 to the 3rd. Notice this is really big. Plus 7. 34,650. Definitely not 0. Now we have to do negative 7. So 2 times negative 7 to the 5th plus 3 times negative 7 to the 3rd plus 7. Negative 34,636. Again, not 0. So then we get to the fraction ones. 2 times 1 divided by 2 to the 5th plus, because I don't have a fraction button, mine are going to look like decimals, and that's okay, because your calculator should be fancier than this one and should be able to keep it as a fraction. 3 times 1 divided by 2 to the 3rd plus 7. Notice that's 7.4 something. Again, all I care about is it's not 0. And then 7 times 1 divided by 2, but negative, to the 5th plus 3 times a negative 1/2 to the 3rd plus 7 is 6 point something, which is again not 0. And then lastly we have the 7/2 and the negative 7/2. Now these don't equal 0, but I can go ahead and show you that. 2 times 7 divided by 2 to the 5th plus 3 times 7 divided by 2 to the 3rd plus 7. All we care about is that it doesn't equal 0. I'm not going to try to write that in there. And then the same thing's going to happen to negative 7/2. This does not equal 0 as well. So if each of these fails to equal 0, that means that from our potential rational root theorem, our list of possible C's over D's, we are not able to find anything that will help us factor this down. So that means this has no rational zeros because this is the only list that we have. It has to be the C over D list. So that means that this one just can't be worked out. It's dead to us. All right. And then in class, we did the very last problem on this, which was example 7, so I'm going to do example 6. How do you use the rational root theorem and how would it be helpful? So this is, again, we're trying to find all zeros of this equation, and it's bigger than x to the 2nd. That's how I know I need to try my C over D list. I don't know how to factor this any other way. It's got 5 terms. We can't even try factor by grouping. So this is my C's and this is my D's. So my factors of my C are plus or minus 1, plus or minus 2, because this is 8, plus or minus 4, plus or minus 8. My factors of D D is 3, so it's plus or minus 1 and plus or minus 3. My actual C over D list, what I'm going to use is all the C's over all the D's. So 1 over 1 would be plus or minus 1, 2 over 1 is plus or minus 2, 4 over 1 is plus or minus 4, 8 over 1 is plus or minus 8. Then I go all of them over 3, plus or minus 1/3, plus or minus 2/3, plus or minus 4/3, plus or minus 8/3. We then try to plug each of these possibilities, which there are 16 here since there's 8 things and they're all plus or minus. We try to plug them in until we find one that gives us a 0. It actually equals the 0 that we need. So if I plug in f of 1, this would be 3 times 1 to the 4th plus 14 times 1 to the 3rd. Always start with 1 and negative 1. That's kind of our general rule. Minus 8 times 1 minus 8. So this would be 3, because all the 1s are just going to stay 1s because they're positive. So 14 plus 14 minus 8 minus 8. 3 plus 14 is 17 plus 14 minus 8 minus 8. That would be 31 minus 16. So that does not equal 0. So it's not going to be f of 1. So now I would try f of negative 1. 3 times negative 1 to the 4th plus 14 times negative 1 to the 3rd plus 14 times negative 1 squared minus 8 times negative 1 minus 8. This is negative 1 to the 4th is positive, so that would just be 3. Negative 1 cubed, though, is negative, so that would be negative 14. Negative 1 squared is 1, so that would be positive 14. And then I get a positive 8 and a negative 8. So we get pretty close, but it's 3 because the 3 out here doesn't get canceled out. So that didn't help us. So we tried 1 and negative 1. We would have to exhaust some more things in our list. So then typically you would try the positive 2 and the negative 2 next. To save some time and space on here, I'm going to use my calculator to plug these in. So you'll just have to kind of watch. Go back up to your equation if you don't remember it, but I've kind of got it in front of me right there with the other examples. So this would be 3 times 2 to the 4th plus 14. Oops, sorry, I need to start over. These calculators are not the best on the calculator. So 3 times 2 to the 4th plus 14 times 2 to the 3rd plus 14 times 2 to the 2nd minus 8 times 2 and then minus 8. So I'm getting 192 on that one, and that's if I typed that all in correctly. But that is definitely not 0. So far, nothing is equal to 0. So let's try negative 2. So 3 times 2, that is negative, to the 4th, plus 14 times negative 2 to the 3rd, plus 14 times negative 2 to the 2nd, minus 8 times negative 2 minus 8. Haha. So I'm going to write this one out a little bit better. So this is 3 times negative 2 to the 4th plus 14 times negative 2 to the 3rd plus 14 times negative 2 to the 2nd minus 8 times negative 2 minus 8. When I plugged that in, I got my 0. So the whole point of this is that once you get a number that works, you then remember do synthetic division with that number. So I take -2, put it in a box, and I write down my polynomial from up here. So 3, 14, 14, -8, -8, and none of the powers were missing, so there wasn't a need for any placeholder. We pull this down, we multiply, we add the column, we multiply, we add the column, we multiply, we add the column, we multiply, we add the column. You should expect that 0. The whole reason of doing this is now we know how to factor part of this polynomial. This guy is x equals -2, and it's a 0, so that means x plus 2 was the factor attached to that if you solve that back over. So that means this polynomial is now an x plus 2 up front, and this is going to reduce down to a third degree because we've pulled out a degree. So this is 3x to the third plus 8x squared minus 2x minus 4, and this is still equal to 0. So now we have a factored portion already done. We are now focusing on this as our next part that we want to break down. So we actually repeat the C over D process for round 2. Now here's something to note. If a number worked in round 1, like the -2, you should always try that number again because sometimes a number works more than once. If it doesn't work again, that's fine. Just go to the other numbers on your potential list. So our list is actually a little bit smaller because remember C used to be an 8. So C is now just plus or minus 1, plus or minus 2, and plus or minus 4. It's just factors of 4. D is plus or minus 1 and plus or minus 3. So so this was round 1. Now we're on round 2. We've eliminated 1 degree from that original polynomial by factoring out the x plus 2. So now we need to find the C over D list for this. So here's my new C, here's my new D. So if I list my list, 1 over 1 is 1, 2 over 1 is 2, 4 over 1 is 4, then we put them over a third, or over 3. So 1/3, 2/3, and 4/3. Notice that now our list is a little bit smaller. We've lost the 8 and the 8/3. And that's because our polynomial reduced. Sometimes that list will be exactly the same if you still have the same C and D. So you just have to look at your polynomial. So now I want to find out if any of these work. So, and again, you're only plugging them in to this new portion, the part you're trying to break down. So this would be, I'm going to try -2 again because we might get lucky. So if we plug in -2, that would be 3 times -2 cubed plus 8 times -2 squared minus 2 times -2 minus 4. So let's try that. So that would be 3 times -2 cubed is -8 plus, that'd be 8 times 4, so that'd be 32. And then that's plus 4 and minus 4. So that does not quite work. So that does not equal 0. Also, I wouldn't waste your time on factors that didn't work before. If 1 and -1 and 2 didn't work before, they still shouldn't work. So that means we're jumping in with 4 now. So if we plug in 4, 3 times 4 cubed plus 8 times 4 squared minus 2 times 4 minus 4. 4 cubed is 64, so that's 3 times 64. And that would be 16 times 8, so plus 16 times 8. So I'm doing some of the math in my head this time. And then that's minus 8 and minus 4. So minus 8, minus 4. Obviously way off. So it does not equal 308. That's not 0. Or, sorry, it doesn't equal 0. So we'll try -4. That's 3 times -4 cubed plus 8 times -4 squared minus 2 times -4 minus 4. That is -64 times 3. Sorry, I put plus, times 3. And then that is 16 times 8 again. So 16 times 8. and then plus 8 and minus 4. So again, not equal to 0. So it looks like it's going to have to be a fraction for this next round. So I'm going to try f of 1/3 and then f of negative 1/3, and we'll have to continue on the next page if those don't work. And we'll have to try 2/3 and then the 4/3 versions. So I'm going to use my calculator again, because once you get into the fraction ones, it's harder to work those out by hand. So we have 3 times 1 divided by 3 to the, because remember we're using this polynomial right here, so to the third, plus 8 times 1 divided by 3 to the second, minus 2 times 1/3 minus 4. So that's negative 3.6-ish, not 0. So we're going to try negative 1/3. 3 times 1 divided by 3 negative to the third plus 8 times 1 with a negative divided by 3 to the second minus 2 times 1 divided by 3 with a negative, and then minus 4, which is negative 2.5. So we're getting closer, but still not 0. So I still need to try 2/3 and negative 2/3 and 4/3 and negative 4/3 to see if any of those work. So I'm going to just go ahead and try to do those without rewriting, and then we can break it down once we find it. So 3 times 2 divided by 3 to the third plus 8 times 2 divided by 3 to the second minus 2 times 2 divided by 3 minus 4. That is really, really close. So f of 2/3 does also not equal 0. So let's try negative 2/3. Maybe we'll get lucky and won't have to do all of the potentials. So 3 times a negative 2/3 to the third plus 8 times a negative 2/3 to the second minus 2 times a negative 2/3 minus 4. And there it is. Yay! So f of negative 2/3 does equal 0. So this one is our next one that we're, oops, let me erase that. There we go. I wanted the blue. There we go. So negative 2/3 is the next one on our list to do synthetic division with. Okay, so here's how this works. When you're in round 2, you take this number that gave you the 0 and you only are trying to break down the cubed part of the polynomial. We already know the x plus 2 has come out, but we do still have to remember the x plus 2 for our final answer. And like I said, we would never give you a 4th power one on the test. We try to stick with a cube like we did in class, so there's only going to be one round. But we need to start with a negative 2/3 in our box for synthetic division. So this is kind of still continuing from above. So negative 2/3, and then our coefficients are 3, 8, negative 2, and negative 4. We already know that that's going to come out to 0. That's what we just spent our time doing. So there's my synthetic division. That's horrible. Let me erase that. Okay. So we're going to pull down our 3, because remember that's how we always start synthetic division. multiply it by what's up in the box. So that would be a -2. Add the column, multiply by this. So that would be -12 over 3, so that's -2. Add the column, multiply. So that's excuse me, I didn't add that right. So this guy would be -2. Add the column, that's 6. -12 divided by 3 is 4. Sorry. I knew I didn't add something right. So -2/3 times 6 is -12 over 3, which is -4. Add the column, then this would be +12 divided by 3, so that's +4, which does give me the 0 we expected. Okay, so let's talk about what we know so far. So we have an x plus 2 that came from round 1. From round 2, we're going to get two things. This guy is going to turn back into a factor. X equals -2/3. You would multiply both sides by 3 because we want to make it back into just a number, and then add 2 over. So this is what this looked like before it got solved down. So 3x plus 2 is another factor, and then remember this guy is my remaining factor, 3x squared, because it was a cube, so now it's down to x squared, plus 6x minus 6. Now what we want to do is we want to finish this out because this is all supposed to be equal to 0. So we already know the solutions to the first two parts. Those are just what we used in our synthetic division boxes. So this guy, x plus 2 equals 0, gives me -2. So there's one of my solutions. This guy gives me the -2/3 we just found. But we had to write it in a factored form so you could see this. So -2/3. This one will either factor or you have to use quadratic formula. In this case, we have to use quadratic formula because this doesn't factor. So this would be x equals -b plus or minus square root b squared minus 4ac all over 2a. So that's 36, and that would be -12 times -6 would be +72, I believe. I'm going to double check that. That's 12 times 6, yeah, 72. And 72 plus 36 adds to 108. So this is square root of 108 all over 6. We do need to simplify this down if we can. So 108, I believe, is divisible by 4. Which would make it, oh, and it's also divisible by 9, so it looks like it's divisible by 36. Let's double check that. So 108 divisible by 36. Yep. This is 36 times 3 underneath there. So that ends up being a 6 on the square root of 3. And then we can reduce all the 6's since everything is 6. So this would be -1 if we divide those, and then plus or minus square root of 3. So my final solution is two separate ones that I get from the quadratic formula. So notice we got 4 different zeros. All of them happen to be real zeros. None of them actually turned out to be imaginary this time, but we never would have gotten this without this rational root theorem because we had a polynomial that we didn't know how to factor. And because of the rational root theorem and a lot of work, we were able to factor it down and find all of the zeros. Now, of course, this method is really cool, but it doesn't work for every single polynomial out there, only ones that have a rational 0. So they have to have at least one 0 that can be written as an integer over an integer. If it doesn't have that, we can't use the method. So that is the end of 4.4. So there we go.